Welcome back to our video module on quantum mechanics. In our previous video, we extended the time-independent Schrodinger's equation in one dimension into a three-dimensional form. And we found that the best way to approach this is using spherical coordinates. And hopefully you've had a chance to play with the Schrodinger's equation a little bit since then using the Laplacian. However, that left us with an interesting difficulty, and that is how do we mathematically approach the wave function when it varies by radius, theta, and phi. Today, we'll be looking at the first step in approaching the TISE in three dimensions, namely separation of variables. So first off, if you've had a chance to play with the Laplacian and the Schrodinger's equation, you've seen some of the difficulties involved with using simply Cartesian coordinates or trying to handle r theta and phi as one function. So we're going to modify our expression of the wave function. First, we're going to take out time. So we have psi of r, theta, and phi. And secondly, instead of using a quantum number here of n, we're going to use a quantum number of k. And k is actually somewhat of a composite of a quantum number n, a quantum number L, and a quantum number m. And for now, we're going to arbitrarily use these, but later on, we're going to see that there was a purpose in our madness. So we're going to take our time-independent wave equation form, and we're going to assume separation. We're going to be looking at a radial function and an angular function. And now all we have to do is take this modified separable format, plug it back into our TISE in three dimensions, and see what the equations look like once everything's been separated. Now I'll leave the actual mechanics of deriving this to you, but what we end up with is some function of r being equal to some function of theta and phi. So we're seeing that this actually is separable, and we assign a value to this. We say L times L plus 1, and this is one of those cases where you just trust me. And as we get further on, you'll see the significance and the value of assigning this, which really is just some constant. It could be anything, but if we assign L plus 1, magic happens later on. Just like we've done with any other separable solution, this means that this is a constant and this is a constant. And if we write those out, we can get a feel for how the wave functions are acting in the radial and angular dimensions. First, in the radial direction, we end up with some derivative of a derivative in the r direction going here, and combined with that, we have something that depends completely on the difference between the potential and the energy of that particular quantum state. So somehow these two combine into discrete states. And in fact, the L times L plus 1 could be any constant, but we'll see that these are actually quantum states, so discrete levels, just like what we saw before with n. Another way to see that is that the potential profile and the energy dictate the types of quantum levels we'll see for this type of radial function. Secondly, we can get a relationship for the radial function, y of theta and phi. Once again, we see that this is some sort of quantized relationship, and we see that over here we have something that's basically a function of theta, and here we have something that has basically a relationship of phi. Of course, there's this influence here as well. But somehow we see that the relationship between the theta and the phi is a quantum relationship of sorts. In other words, in this case, second derivative being an indication of curvature, the curvatures move at quantized levels from 1 to 2 to 9, whatever the case may be. We'll learn more about that later. The second takeaway here is notice that there is no energy. There's no potential energy, that this radial equation seems to have no direct relationship with the potential profile or the energy. Here you can start to see the value of this type of separation. So hopefully this has given you a quick introduction into how and why we separate variables into radial and angular components, and you have a better intuition of where this math might be going and its relevance to three-dimensional models. This is amongst our first steps into a really rich topic, and I look forward to seeing where this goes. Thank you, and I look forward to our next video together.